This next part's a little tricky in terms of how to visualize it. So what we have here, we have topography. So you can see the contour lines are these solid lines, and so that you see there's a hilltop here at 380 feet or a little bit higher. Then there's a valley, and then you go to up another hill or slope over here. And note the rule of V here for contour lines. So these are pointing uphill, so there's a little valley that's going down this way toward the south. Now these other lines are showing the elevation of the water table in the subsurface. And so remember, the key thing is whenever the water table intersects the ground surface is where we're going to have springs or water flowing on the ground, like this idea of artesian, flow. And so to do this, we need to plot where the two sets of contour lines intersect. And so let's see if I can zoom in a little bit here. And so to do this, for example, we got 320 down here. Nothing's going on there. It's not really intersecting. So 320. So these are 10-foot contour intervals for the contour lines. So it looks like 320 is right here. So the 320 groundwater contour intersects the land contour right there and right there. So they both intersect right there. Then if we look at the 330, which is this one, you can see they intersect right there and right there. So I'm just plotting where they intersect. And then at 340, so here's 340, so they intersect there and right there. So let's just keep plotting these as we go along. 350, so here's a 350 intersect here and over here. Whoops, where's 350? Right here. And 360 intersects here. And let's see, where's the other 360? This is 360 right here. So we'll go to 370, which is going to be over here. And the 370 is right here. And then note that we don't have an intersection for 380, right? And in fact, if we go farther this way, we see that there's another 370 right here. And if we go back over this, there's another 360 over here. And then there's another 350 way out over here. All right, so now if we connect these points, something like this. So you're going to want to do this on your lab. So where would water flow? Obviously, we know that the creek is flowing down in this direction, right? The creek is flowing down in that direction. So that means that water is going to start seeping out of the ground. Water is going to be seeping out of the ground in this direction. So in these areas down over here, and obviously in here, that's a hilltop. It's going to have to seep around and move over in this direction down to this creek here, right? Yeah, that makes sense here because the higher elevation is up over here and the water is going to be flowing down in this direction here. So that's the line you want to draw. So it wants me to shade in the area of the map where wells would flow at the surface, right? Flow at the surface. Yeah, since these are higher elevations over here than actually you would probably want to shade in this upper area over here because water is going to be flowing out of there in that direction and then flowing down into the hill. So that's kind of what we're looking at there. It's a little confusing because of the topography here. We have this hilltop here on the left and a valley, then another hilltop. But the key thing to do here, let's delete that part there, is make sure you have this line drawn and make it kind of match there. Have that line drawn, and that's where you're seeing the water table intersecting the ground surface, and that's where you're going to see the flow. All right, so as we go along here, the next part here deals with the Santa Clara Valley and this idea of subsidence. Remember, subsidence is if we withdraw too much groundwater faster than we're allowing the rain to recharge the aquifer, what's going to happen is that the sand grains or just because there's overburdened rock pressure, we call it lithostatic rock pressure, lithostatic pressure, will cause the porosity to be reduced. In other words, the sand grains in the aquifer will shift closer together, compact, and when that happens, the whole land starts sinking, and that's what we call subsidence. And note that the subsidence is occurring mostly in this alluvium and the softer sedimentary younger deposits here in the bay. And note that for consolidated sediments, this dark area here, there's no subsidence because that rock is already consolidated. It's not going to collapse, right? And so that's one of the questions I ask about that. The first question is, where what part of the Santa Clara Valley has had the greatest subsidence. So you can see that we've had about 8 to 9 feet of subsidence in both Santa Clara and San Jose. That'll be the greatest. And then what has been the total subsidence between 1934 and 1967? So what you want to do here, you take the 12.7 feet and subtract 4.6, right? And that'll be the total subsidence between that time here. So you put that answer there. What is the average annual rate of subsidence between 1934 and 1967? So in 1930, so again, you're doing the number of feet here, but now you want to divide it by the number of years. So figure out the number of years between, so what is it? That's 33 years. So take this feet and divide it by 33 years, and you get this answer for the annual average rate. So do that. Now looking at the Santa Clara Valley map, what places in Santa Clara Valley would subsidence cause the most problems? If we start drawing more groundwater out, although we're not doing that now, we're Santa Clara Valley used to be famous for its orchards. So we're lots of orchards, and we're withdrawing lots of groundwater, and that's led to all the subsidence. Now we're not. It's a Silicon Valley, so we don't have the orchards. And so the subsidence has stopped, and we're actually several places like Vasona Creek over here, Vasona Lake and Los Gatos, and there's some ponds down here near South San Jose, near Morgan Hill, which we're allowing water to try to recharge. They're called infiltration ponds, trying to kind of keep the subsidence from occurring anymore. So we're not going to really see that anymore. But if we were to continue, note that towns like Agnew, and there's a town here called Alviso. So Alviso and Agnew, what would happen is the bay waters could flood them. That would be the problem with more subsidence. And then here's that question about the darker areas. And then the last question, or not the last, but question 6. So 9 feet in San Jose. So again, here what you want to do, what was the average rate of subsidence for the 7-year period between 1960 and 67? Take the difference here. So it's like 3.7 feet divided by, so you take 3.7 feet divided by 7 years to give you this answer between 1960 and 67. And now the next part here looks at this hydrograph. And the key thing about this one is this LS means the land surface. And then this is feet above land, and this is feet below land. And over here is the amount of subsidence over time. What was the level of water in the well, the San Jose well, in 1915? So you can see 1915 is this number here. And you can see that the water level was in the positive range. Maybe, so if that's 10 feet, maybe it's about 2 feet. And here toward the end of 1915, it got maybe up to 5 feet, 10 feet. So 2 to 10 feet, I would say. 2 to 10 feet would be there. And in the positive range, above the ground surface. So obviously that would be artesian, right? Because there's a potentiometric surface, the hydraulic pressure. And then in 67, it's down here at negative 180 or so, negative 180, right? So that's what the hydrograph is pointing out there. And then, so during what years was it artesian? You can answer that. And then what are these minor fluctuations? And if you look at the years here, since each of these covers about 5 years, right? So there's 1, 2, 3, 4. There's 5 peaks per year. So that would be like winter, rain, summer, withdrawal. Winter, summer, winter, summer. So basically it's the rainy season and the dry season. Rainy season and dry. So that's what it's really showing, these peaks and valleys there. And then let's see what we have here for 10. So if you drew a line from 1915 to 67, that line would be the slope of the average annual subsidence over time. However, you can see that between 38 and 45 here, we had actually a recharge, which means for this time period between 38 and 45 here, we were not withdrawing as much groundwater. And so the groundwater was allowed to infiltrate, and we reduced the subsidence. So what was happening during this time? I think that's a question. So for this one, we're saying that there was a positive recharge, right? So you can word this in your own words for number 10. For number 11, there was a global event that occurred during this time that had a lot of people doing something else other than agriculture. So maybe you can kind of try to figure out what's going on there.